Okay, this video has to do with laboratory number 1 for BBE 3012. In this lab we're going to be measuring surface tension and the density of water. So we're going to be measuring the surface tension of water and density of water. And we're going to be using a couple different methods for measuring each of those properties. The first method, or the first measurement we're going to make, is the measurement of surface tension, and that we're going to do using a system that's somewhat analogous to what's shown here by this balance beam. We have a counterweight located here, and we've got a pin that's connected to a string, and what we'll have is that the pin will be submerged just below the water surface in a container here. The container is going to be right here. The pin will just be below the water surface, and we'll add weights in here. Once the thing, starting off with it being balanced, we add weights in here to the point where the upward force that's on the string that's caused because of the weight of the pins will pull this needle out of the water. The force that's required to do that, that is this force here, this is acting downward. The force that causes that to happen is going to be associated with the surface tension of the fluid. So the procedure is spelled out here that you have to do, that you're going to be using. We're going to use small pins for which we'll find out what the average mass is of each of the pins. So you'll use maybe 10 pins that you'll put into on a scale and determine the weight of those pins and determine then the mass of them. So you have an average weight of the pins. We're going to then set this balance beam up so that you can get it balanced with the needle on it. So you'll determine how many pins that you're required to put into the cup that's on the balance beam, such that it just balances the balance beam against the weight of the needle hanging in airspace. Following that, you'll then fill up a beaker with water up to a certain point, such that it will just submerge the needle that's on the end of the string. You don't need it. You don't want to have it the beaker filled up entirely. You want it only to be such that it'll only start to barely submerge the needle. You'll then add pins to that cup to the point where the needle is pulled out of the water, and the number of pins that's required to do that will be associated with the force that is required to pull the pin out of the water, and that force then will be used to calculate the surface tension of the water. The relation that you use for that to calculate the surface tension is given here. Capital F is the force that's being applied to pull the needle out of the water. D is the length of the needle that is being pulled out of the water that's connected to the string, and in here sigma is the surface tension of the water. It's the surface tension of the water that's being used. One caution here is that you want to make sure that you are measuring surface tension and not just an attractive force between the needle and the water. So here's a little explanation for that. When the needle is pulled out of the water, it should look like it has some moisture on it. If it doesn't, then probably you weren't really measuring the you weren't actually measuring the surface tension of the water. So you'll do this both for the case where you have tap water and then for the case where you have water that containing soap. Soap will decrease the surface tension of water, and thereby you should require less force for the case when you have the soapy water. We're going to measure the surface tension, or indicate the surface tension, by another method, and that will be using laboratory slides, which are shown in this image, this photograph. These laboratory slides are set together with a certain material that has a specified thickness, so that the here in this case, for instance, we've got metal strips on either side. You got rubber bands that hold the glass slides together. And these metal strips maintain a space between the glass slides. You'll then and we're going to do this for the case where you have a paper clip, aluminum foil, these metal strips, and then these longer metal strips that have a larger thickness to them. The actual thickness of these materials that are being used, which determines what the spacing is between the glass plates, is given to you in the laboratory description. So you'll have that information. So we'll know what the actual spacing is. You'll then take the glass plates as set up here, and you're going to dip that into water that's got a dye in it. We have the dye so it's easy to see the water that rises inside the glass plate. You'll put the glass plate in vertically into the water and submerge it to a certain depth, and what you expect to see then is that the water will rise up inside of that. It's not going to be uniform all the way across the plate. There are a number of reasons why that might occur, that it wouldn't be uniform across there. But what you're going to want to know is if when you dip this in, let's say that the water level in the container that you're dipping this into is here, the water then is rising to this height above the water surface. That is the height of capillary rise that you're going to be measuring. We'll call this H. So you're going to be doing this for each of these different cases, both for the case where you have tap water and the case also where you have the soapy water. Okay. Then what you're going to do with the data that you have from the experiment is that you're going to take the surface tension you measured in the first case with the balance beam, that is the values of surface tension that were measured, and you're going to see how well you're able to predict the height of rise that's measured with the glass plates. Here's the unit weight of the water. Here's the contact angle for the cosine of the contact angle. Here we'll just make the assumption that theta is equal to 0 degrees. Cosine of 0 is 1. The predicted value of HC, that's the height of rise that you should expect to see in the, within those glass plates. And here we're using the measured sigma value from the balance beam for both the tap water and for the soapy water. The question is, how well does this equation predict the actual height of rise that's observed in the glass plates given the values of the surface tension? Now in this formula we have R1 would be the radius of the curvature of the meniscus parallel to the slide plates, and R2 is the radius of curvature normal for the meniscus normal to the slide plates. The meniscus that is parallel to the slide plates will have a very large radius of curvature. We might basically treat R1 as being infinite. So 1 over R1 then of course is equal to 0. the radius of curvature normal for the meniscus, normal to the slide plates, is just 1/2 the spacing between the slide plates. So if these are the glass plates, this is the meniscus between them, and if this is the distance between the plates, then we'll just say that R2 is equal to D over 2. In the final part of the experiment, we're going to measure the density of water that is either tap water or water that's got two different concentrations of salt. One concentration is exactly 1/2 that of seawater, and the other is equal to the concentration of salt in seawater. Now what we're going to do here is we're going to make the measurement in two different ways. One will be, we will take a mini pipette from which we're able to measure how much volume of water we are putting into a beaker. With that beaker, we're going to weigh how much water is actually put into the beaker, and by knowing the weight and the exact volume of water that was placed into the beaker, we'll be able to determine the density of the water. So that one's pretty straightforward. The accuracy of the measurement, of course, is related to the accuracy of the mini pipette or micro pipette, and these micro pipettes that we'll be using are quite accurate. So we'll have very high resolution on the volume, and you should be able to get a good number on what the densities are. Of course, the density of the water increases as the salt concentration goes up. The second method we're going to use is a hydrometer, and we're going to do this using placing, we have water that's already inside of 3 different graduated cylinders. One water is pure, or tap water. One's got 50% salt, and the other one's got 100% salt concentration, 100% seawater salt. And we're going to use a hydrometer to make measurement of the density. Now, for the hydrometer, basically what we got in this situation is like this. We got these graduated cylinders, and we got a water level in here like this, and we'll be placing the hydrometer down inside of the water, and we'll be measuring on it the reading, or we'll be recording the reading that you see on here. There are markings on the side of the, or on the surface of the stem of the hydrometer. You'll be recording those numbers for each of the 3 cases. So you'll just take the hydrometer, place it first in the first graduated cylinder, take the recording, move it to the next one, and so forth. And what you should see is as the water has more salt, the hydrometer should be higher, float higher in the water, just because of the buoyancy effect. Now, we've measured the volume of the hydrometer. So we've got this bottom part of the hydrometer, which has got lead in it, and then we've got the stem here, and there's a 0 point on here, and then above that a number of markings. And what we've done is we measure the volume of water that's displaced when we put the hydrometer in to the first marking, or the first division that you see on the hydrometer. So we know exactly how much volume of water is displaced by that. That tells us what the volume is of that portion of the hydrometer. And then we also determined how much volume is displaced for every one of these increments. As you push the hydrometer into the water, how much change in the volume displaced occurs. And that is all explained in the appendix right here. So the hydrometer has a total mass of 60.95 grams. Displaced fluid, yeah, this was done in the BAE room 315, or that the hydrometer came from that room. And this just shows the results from the experiment that was done to determine the volume of the hydrometer. Water level without the hydrometer was set at 168 milliliters. The water level with the hydrometer fully immersed to the zero line on the stem is 229 milliliters. The water level with the hydrometer immersed only to the 60 line on the stem is 226 milliliters. For full immersion, the water displaced then is 229 minus 168, or 61 milliliters. For immersion just to the 60 line, the water displaced is 58 millimeters, which just basically means that for every every division of submersion of the hydrometer, your amount of displaced volume is 0.05 milliliters, this number here. So if we know how much displacement it is, we know what the change in buoyancy is associated with that.